Hello, hello. It's time for lesson 3-7 on something called direct variation. Two quantities, x and y, we've been dealing a lot with x and y this chapter, huh? They show direct variation when the value of y is equal to k times x, where k is a number that is not equal to 0, because if k was equal to 0, then y would just equal 0 and there wouldn't be an x. There has to be an x, always. Direct variation, it's just another way of saying that a proportional relationship exists. This whole chapter has really come back down to that proportional equivalent relationship between the two. So we're going to learn how to identify direct variation from a table, from a graph, and from an equation. And basically, if it can be written in this form, we're good as far as equations go. And it all kind of links back to everything that we've been talking about, which is pretty cool this unit. Okay, so I'm going to be giving you tables, and I'm going to ask you, does this table show direct variation? Is there a proportional relationship going on? And the way to tell from a table is that as x doubles, triples, quadruples, etc., y does also. Okay, so here's what I mean, and you need to check a whole bunch of them to make sure. Okay, here's x, and don't worry about the 0 for now, because when you multiply 0, it doesn't do anything. But doubling means multiplying by 2. So as I double x times 2, 1 times 2 is 2, right? If I double y, is 10 times 2, 20? Yes. If I triple x, 1 times 3 is 3. Is 10 times 3, 30? Yes. 1 times 4 is 4. Is 10 times 4, 40? Yes. So as x doubles and triples, so does y. Another way to tell by looking at a table is you could use the cross products property, because we know that in a table we can create ratios or proportions just by drawing lines and setting it up. We learned that in lesson 3-5. So 1 times 20 is 20, 10 times 2 is 20. It'll work here too. 2 times 30 is 60, 20 times 3 is 60. 3 times 4 is 120, 30 times 4 is 120. It'll even work if I cover these up. 1 times 40 is 40, and 4 times 10 is 40. So the cross products property will work in any that you choose. Also, this is kind of cool. This is 1/10, right? What does 2/20 simplify to? What does 3/30 simplify to? What does 4/40 simplify to? They all simplify to the same thing. So you don't have to check using every single one of those ways. If as x is doubling, tripling, quadrupling, y is doing the same thing, that means that all the rest of this is going to be true. So this would be a yes. All right, in this one, as I go from 1 to 2, 1 times 2 is 2. Is 60 times 2 70? No. So right there you can already see that this one doesn't work, because as x doubles, y doesn't. You could also use a cross products property. 60 times 2 is 120, but 1 times 70 isn't. And if we're trying to simplify this, 1/60th is in simplest form. 2/70ths was simplified to 1/35th. So in this one, this would be a no, because as x doubles, triples, quadruples, y does not. And if you check it using cross products or simplifying, you'll see that nope, a proportional relationship doesn't exist. So there is not direct variation. All right, so that's how you can tell from a table. When you're looking at a graph to determine if there's direct variation, two things. The graph needs to be a straight line so that there's a constant rate of change going on, and the graph needs to pass through 0, 0. Or even if you're not given that piece of the graph, if you're only given, let's say, some chunk up here of the graph and you can't see 0, 0, the graph would pass through it. So I ask you to plot these points and tell me which one is direct variation, if any. So the first table that I give you, let me zoom out a little bit so we can do this. I give you a whole table full of points, and we're going to plot these points. So x, y, these are just ordered pairs, remember. When x is 1, y is -2, that's all this is saying. And this is my x-axis and this is my y. So 1, -2 means over 1 down 2, 2, 0 means right 2, down 0. 3, 1, 2, 3 to the right, up 2. And 4, 4. So there is our nice straight line. Now, this is a straight line. That's one of the criteria. It says that it's going to pass through the origin. Is there any way that this line can stay straight and somehow ricochet back up here to touch 0, 0? No. So because it doesn't touch the origin here, it's a no. And honestly, you could have identified that beforehand, because in looking at the table, see how it says 2, 0? That means that there's no way 0, 0 is going to be on here if the 0 is already taken right there. And if you look at cross products, 2 times 4 is 8, 4 times 3 is 12. So you can even tell just by looking at the table. Still good practice to plot out the points though. All right, next one we'll do the same. Let's plot out -2, -3. So that means 2 to the left, 3 down, because it's x, then y. There's our 0, 0. Over 2, up 3. And then 4, 6 would be over 4, up 6. We'll draw a nice straight line through all of those. And as you're looking at this graph, we see, hey, this is great. This is a nice straight line, and it does pass through 0, 0. So because it's straight and passes through 0, 0, this is a yes. So if you're just looking at a graph, if I said, which graph shows direct variation, and looking at these two graphs, we would know that this one does have direct variation because it passes through 0, 0 and it's straight. And this one does not have direct variation. Even though it's a straight line, it will never be able to pass through 0, 0. All right, continue along. Now we're going to examine direct variation from equations. So I already said in the intro to this that the equation is going to be in the form of y equals k times x, where k cannot be 0. And the equation has to be solved for y in order to figure out if it's direct variation. So if you get an equation that doesn't have y by itself, you need to use what you know about solving equations to isolate the y, to solve for that y and get it by itself. So I show you 3 examples of equations that would represent direct variation, and then I give you a few non-examples. I want to tell you why each is what it is. So first off, right here, y equals 10x, this is direct variation. And in this, the y and the x are always going to stay letters. K is going to be replaced with a number. So anytime you see y equals some number times x, that's direct variation. So this is a perfect one. Now this is also an example, and you might be thinking, but y is not by itself. Well, once you get y by itself, and how do you get rid of a fraction when it's being multiplied by a letter? That's right, we can multiply by the reciprocal. So the reciprocal of 1/2 is actually 2 over 1, or just 2, same thing. Those all cancel out. Y is by itself, and 2 times x, or x times 2, is 2x. So you see, once we get that y isolated, it's in the form of y equals some number times x. That means, yes, it's direct variation. All right, and this one, it's solved for y to start. I'm sorry, it's solved for x to start. And this is an example of direct variation, and you'll see once we get it solved for y. I want y by itself. It's being multiplied by 4. I'm going to divide by 4. So y equals x over 4. Now you might be thinking to yourself, well, wait a minute. The equation is supposed to be y equals some number times x. That shows x being divided by 4. This is actually a number being multiplied by x. When there's not a number in front of an x, what's really there? Hopefully you're saying a 1. So when you have y equals x over 4, what you're really saying is that y equals 1/4 x. And the only value that k can't be is 0. 1/4 isn't 0, it's just a fraction. Fractions are allowed. So this is an example of direct variation. Now I'm going to show you some non-examples so you can see the difference. All right, in this first one up here, it says y equals 10x plus 50. So right here, if it was just y equals 10x, we'd be great. But because this extra number is being added here, it's not going to have direct variation. This graph isn't going to pass through 0, 0. It's actually going to start at 50. We'll talk more about that in chapter 10. So right here, not direct variation. because it's not just y equals kx, it's y equals kx plus something else. All right, this one, we might be thinking, oh yeah, that works. There's a number times x. Well, y is not isolated yet. To get y by itself, we would have to add a negative 1 to each side. So y really would equal 2x plus negative 1. So again, that plus negative 1 being added to the y equals kx means that it's not going to show direct variation. All right, one more non-example here. This one I have x times y equals 3. I would like the y by itself before we decide, right? So we're going to divide by x, and y would equal 3 divided by x. Okay, now the x is in the denominator spot. This isn't the same as when x was in the numerator. This can mean 1/4 times x because the x is in the top spot. It's 1 times x over 4. With this, even if I put a 1 in front of the x, it would be 3 divided by 1x. And I'm supposed to be multiplying the 3 and the x. So if I'm dividing by x, that's not going to work. So if you see x in the denominator, it's a no. That's not direct variation. So in summary, this would make a nice constructed response, just saying, hint, hint. If you're trying to determine if a relationship shows direct variation, if as x doubles, triples, etc., y does too, that's one way to tell. If its graph is a straight line that passes through 0, 0, that's another way to tell. And if the equation can be written in the form of y equals kx, where k is not equal to 0. So this is how you can tell from a table. This is how you can tell from a graph. And this is how you can tell from an equation. And all three of those things have a very solid connection. We are done. See you tomorrow.